Here is my big summary slide. This is my cheat sheet slide. Let me pull up now in my helicopter and even go higher to give you a 30,000 foot view of thermodynamics on the whole. And you can tell what I'm doing with the intro for thermodynamics is I'm giving you the big picture so that when you start getting down in the forest and chopping through the weeds, you'll already have the big picture. Okay, so here's what I got from my lab and from my experience and from textbooks and everywhere I could find it. My gift to you. Thermodynamics. First of all, there's 3 basic thermodynamic terms we would deal with in this class. There are more than this, but these are the 3 we care about. Delta H, which is heat at constant pressure. Delta G, which can be thought of as the total energy under constant pressure. And delta S, which is your entropy term. That's your work term. So think about this as total energy, heat energy, and work energy. I put those in quotation marks because that's not technically true, but that's a good way. So delta U is equal to Q minus W. Delta G is equal to delta H minus T delta S. So we'll get into that later. But you now see this is your main thermodynamic equation. There are 5 ways to get at delta H, delta D, or delta S. In other words, what you need to know for a test, since you're not going to actually run a reaction in a test, but you will be given problems. And typically it's either the 2 types of problems, you're going to use, hang on, oh, I got too much technology going here. Okay. The marvels of online live teaching. Okay, so what you care about for the test, you're not really going to do this on a test. So if you're 2 types of problems, you're going to be given these and asked to calculate probably the energy or something else, or you're going to be given something else and you're going to be asked to calculate these for the reaction. Those are basically what's going to happen. Okay. Turns out there's about 4 ways to skin that cat. Why anybody would want to skin a cat? I don't really know, but there are 4 ways to do it. 1, you can look at bond energies. And we'll go over each of these either here or in the lab. Okay. Or you can look at enthalpies of formation. Or you're going to use Hess's law. Or you're actually going to use the relationship delta G equal delta H T delta S if you know any. There's 4 variables here. So if you know any 3, you can calculate the 4th one. So this is essentially all this chapter is. It's giving you data, giving you different types of data, and you ferreting through using critically to think about what data you have and what approach you can use to get to the answer. That's your 30,000 foot view of what you're going to do. And what happens in the textbook and what happens in the lab and what happens in lectures is they'll start and we'll talk a little bit about this. Ooh, it works better with my mouse. Are this, and you're going to calculate those. Yes. And I know I'm beating a dead horse a bit here, but okay, well, that's just what we're going to do, so I can say, or you're going to be given this, and you're going to calculate one of those. Yep, there we go. That's basically in a nutshell. And so we're going to learn how to do those. Okay, everyone clear? Kind of, sort of, maybe. Okay. I don't know. There it is. Okay. Right. So let me give you an overview. This just now, instead of 30,000 foot, let me drop down to about 10,000 feet. And then we're going to jump down in the weeds and start hacking through some of these. Okay. Just because you may want to refer back to this. This is a really handy diagram. Okay. Bond energy. What do we mean then? Here's what you're going to be taught. The delta H for a reaction is equal to the sum of all of the bonds that you break minus all of the energy that it took to form those bonds. That's it. So in other words, you can actually calculate this for an entire reaction just looking at things at the bond level. Well, guess what? You can also just look at things at the molecular level. Okay, that's my phone in case you're wondering. All right. It'll go away. Okay, at the molecular level, delta H for a reaction. And by the way, this could be delta H, or this could be delta S, or this could be delta G. Any one of your three thermodynamic parameters. And that's something to remember, as I sidetrack myself again, that anytime you see something for one of these thermodynamic parameters, it probably applies for all three. Okay? Normally, things are taught in terms of delta H because you know it's heat and you're comfortable with the heat, and it's easy to visualize heat, and who knows what Gibbs free energy is, and who knows what entropy is. So they teach these things for heat and then say, oh, by the way, they apply for delta S and delta G too. Just thought you'd like to know that. Okay, so when I put delta H, it can be anything. So delta H is the bond energy's broken minus formed, okay? Or another way to put it, the bond energy of all the reactants minus the bond energy of all the products. So guess what you're going to be given? A table of how much energy each bond type has. Guess what's going to be discussed later? How strong a bond is and how weak a bond is. Who cares? Well, you do if you want. You do if you're asked one of these questions. You do if you're asked one of these questions and you're only given bond energy information, then you better know how to get that so you could get to your answer. That's why you care. Okay. We can also look at things at the molecular level. So think about the progression. You have atoms. Atoms go together to make bonds, so that process has energy. Or bonds go together to make molecules, so you can look at things at the molecules. Or molecules then all react to make equations. So my little device I figured out is, hey, you can calculate these from any type of information. You just got to know where you're at. Okay, so there we go. So later, then after I don't remember which order, then we're going to talk about the molecular level, which is delta H that it took to form all of your reactants is also equal, if you subtract the heat it took to form all of your products, you'll get the heat for a reaction. Well, this kind of makes sense in a way. And we'll look at this again. So you have reactants here and you have an energy diagram, right? So there's your reactants and it took a certain amount of energy to get to the products. So there's your reactants and there's your products. Yep. So it took a certain amount of energy to form these. It took a certain amount of energy to form these. Well, duh. Guess what the energy of your reaction is? I know. The total amount of energy it took to form these minus the total amount of the energy it took to form those. Hey, that is my reaction. Heat for the reaction. So it's kind of cute. That's just kind of a picture of what that means. Okay? Finally, you can do the old Hess's law thing, which is because it's a function of how you got there. Let's look at that. And then we can move a lot quicker because I'm giving you an intro. Okay, so we want to know delta H for the reaction. Well, let's say I know the reaction for how to form CO2. I know that's minus 111. Well, guess what? I could do this in 2 steps. I could go from carbon to carbon monoxide and then from carbon monoxide to dioxide. And when I add these two together, 349 minus 283, this one was obviously exothermic and this one was obviously endothermic. When I add those up together, guess what I get? Oh, I get 111. Why? Because it doesn't matter if I climb straight up the hill, reaction 1, or if I fly way high and then I come back down. I end up at the same point, which is, let me take a different color, which is this. Yep, that's my total. There we go. So that's cumulative. That's called Hess's law. There's the one that it basically says all this is additive. Okay. That's a backdrop of basically everything we're going to do in thermodynamics. So now let's kind of jump down in the weeds a little bit. Okay, the first thing is, just like thermodynamics, you've got to know what your standard states are. Why? Because we don't know how much energy something has. The only thing that's absolute is temperature. We know there's an absolute temperature, 0 Kelvin. Everything else you can't. So what we're going to do is we're going to reference things from a standard state. Because what we really have is we need to know what delta G is. We can't measure G for a system. We can't do that. So what we do is we make systems change, and then we measure that difference. That's how we get into it. We don't know G for this, and we don't know G prime for that state. We don't know it. We don't know it. Why? We can't measure it. I don't know. We don't know it. But guess what? I can dang sure take a starting point. I can take an ending point, and I can measure the difference. So that's the well. Then what's your 0 point? Okay. So what is G here? Something has to be 0, right? It's like temperature, degrees Celsius. We define the freezing point of water as 0. Well, it's not 0 degrees temperature. It's 373 Kelvin. It's got a lot of energy. I know. But I had to reference it something. So I just arbitrarily said the standard state for 0 degrees Celsius is going to be the freezing point of water. Boom. I could have chosen 0 to be the boiling point of water, but it didn't. I had to drive a stake in the ground as some reference point that now I know what my 0 point is. And I can measure every temperature now as a fluctuation from 0 degrees C. And I could use delta. And there we go. And if that's 0, no matter what my distance is, in Kelvin, I don't care. It's still going to only be 20 degrees C. Why? It's not that true. But if the freezing point of water is 0, as I move from that, I can just declare that number as whatever it is because the other end, freezing point of water, is 0. Okay. So you probably understand the concept of standard states, but there we go. Okay. So what is thermodynamic? What is a standard state? Okay. And I just told you that reference point. So the standard state for a gas is 1 bar. Okay. Basically 1 atmosphere. Okay, 0.987 atmosphere. Close enough for government work unless you're working to several sig figs. I normally just take the standard state as 1 atmosphere. Okay, how about for a solution? An aqueous solution. Well, it's 1 molar. So anything that's 1 molar is no longer at 0 degrees C. Any gas that's at any pressure other than 1 bar, 1 atmosphere, it's no longer at 0 degrees C. It's at something else, okay? But how about a pure solid or pure liquid, okay? Well, this sounds hey, doesn't this seem a whole lot like your standard states earlier? Yeah, it does, okay? That's used for equilibrium. Okay, key point. Alert, pay attention, alert. This little thing that looks like a degree symbol, yes? Okay, it's actually not a degree symbol. I didn't know it. There's a name for that thing. It's like smaller and up a little higher, lower. I don't know what it's called. One of you English wizards might know. But anyway, so that little degree symbol in quotation marks, that indicates standard state. So notice, if I tell you delta H and I put you see a little dot there. Don't blow that dot off. That's pretty important. That's telling you that you're talking about delta H at standard state. Well, what does that mean? Oh, by the way, yeah, it means it occurs under standard state. You have a standard temperature, 298. So the standard state is this. Your standard temperature is 298 Kelvin, or 25 degrees C. Ruh-roh. Because earlier, when we did some things and we talked about standard state, guess what your standard state temperature was? 0 degrees C. So this is a definite pay attention alert. So what's a standard state in chemistry? Well, we have 2. It depends on what you're talking about. If you're talking about some things, the standard state is 0 degrees C. If you're talking about thermo, standard state is 25 degrees C. Yep, 298.15. Okay, you're sufficiently clear on that. You gotta know that. There are 2 standard states, so I guess the standard state is not so standard, is it? Okay. It's like equilibrium constant that changes with temperature, right? It's kind of an oxymoron. Okay. This is not taught in the book, but it's implied. It's kind of a sticky wicket. So what is a mole reaction? Okay. Right. It's going to be hard to explain this. It's going to be easier when you see it. But basically, for a mole reaction, is basically getting back at this point that a mole reaction means whatever reaction you're talking about, the mole reaction is how much it is for the reaction run with the number of moles you show for that reaction. Told you it's hard to explain, so let me go back. Okay, so go back to, okay, so each of these, if I do this, minus 286 kilojoules is the mole reaction for this reaction. Okay, and minus 272 is the mole reaction for this reaction. So if I change these, if I start out with this and tell you the mole reaction is this, if I then do something to change this amount, you have to change this amount, right? So the mole reaction just means the heat for the reaction that's stated. The mole reaction, the moles for the reaction stated correspond to that. Okay, because, okay, so what does H2 have? Right, it's got a molar mass of 2. A mole has 2 grams. What if I have a question though and I don't start with 2 grams? What if this is the reaction we're working? Yeah? And we say, well, this is what it is for a mole. But let's say I only start with 1 gram in the real world. Well, guess what? When I work this out, this isn't going to be 2. This is my mole reaction. So if I use 1 gram, I've got to do some calculations to show this is going to cut in half. This is my mole reaction. My new one is not the mole reaction. Yes. Okay. So the only way this is the mole reaction if I start with exactly 2.0 grams. Then this would correspond to the same value as the mole reaction. Okay. We'll work through those and it'll kind of start to become clear. Or maybe. Okay. These were all why I'm taking so much time to go over this, almost apologetically, is that my instructor didn't tell me this stuff, and it was just a nightmare trying to figure all these tripwires out on your own. You can just spend hours and you trip over it before you finally realize, oh my gosh, that little dot, I should have been paying attention to that. Or, oh my gosh, every time I see that, I know the temperature. Oh, now I know why temperature wasn't given, and they worked the problem. Because they knew it was 298 because there was a little dot there. Yeah. What else do you know about it? If there's a dot there. You know, these things are probably true. Okay, so anyway, so the way to not do this is to just muddle through like 1,000 problems and figure these out on your own. Okay, but hey, that's the way they did it at UT back when I was there. Okay, spontaneity. So now what the book does is, okay, that's supposed to be the review. By the way, that is all your review. Everything we just covered was supposed to be review. Okay, so at any rate, so let's pick it up. Thermodynamics. Okay, so now you know all about delta H and you know the overview. So we can go quite a bit quicker. Matter of fact, if I stopped here, you could probably read the book and do the rest of it, hopefully on your own. Okay, so I'm going to move quick. But this is an important, very important concept. I've touched on it earlier. I told you it was coming. I introduced you to entropy earlier, but here we go. The whole punchline of these, most of these problems, a lot of your questions go say, is this spontaneous or not? So what does spontaneous mean? Does it occur naturally? And this is that ball on a hill thing. Does a ball naturally roll downhill? Yeah, it's spontaneous. Does a ball naturally roll uphill? No, it's non-spontaneous. Well, guess what? You can't look at a chemical reaction when I mix two things until if it's going to go or not. Is it going to go? Is it downhill? Or is it not going to go? Is it uphill? Well, there it's not so obvious. That's why you have thermodynamics. Okay, so the first thing I want to tell you about thermodynamics, or another thing, it's like the equilibrium. Just to clarify, we are dealing with the difference. The delta G is normally, that is so bad right there. Let's try this again. Let's see if it'll, remember, that was kinetics. Yes? So what we're dealing with, the delta G or delta anything, is reactants minus products. Where you're going to, products minus where you started reactants. Got it? So we don't know what's happening here. But so thermo deals with this. This is the world of thermodynamics. Okay. Please don't lose this point. Okay. So this is why chemistry final is so hard, because at the end you're going to learn this. So remember, I'm just looking at the difference between the two. That's what the delta means. This is the initial state. That's the final state. With me? Okay. So there. So something that's spontaneous, at least thermodynamic, means what? It's downhill. You see where diamond. Actually, there's a saying that says the diamonds are forever, and that's just a lie. It's just a lie. It's just a bold-faced lie. They're not forever, okay? Because actually, diamond has a higher energy than graphite, and given enough time, all diamond will degrade down to graphite. Okay, well, it's not a lie from a practical viewpoint. Why? Well, because I need a different color. Because this hump, as you know from kinetics, for diamond is like really, really high. Yep. And it just so happens, so few diamond particles get over this hump that this occurs, I don't know, billions, trillions, quadrillions of years. So it is really, really slow. But it's not forever. Forever is a pretty long time. Okay, so there we go. So practically speaking. So I like to use this to just show you the downhill. Okay, so in other words, is the change from diamond to graphite spontaneous? And the answer is yes. Now here's what you would find out too. And we're going to see this in a little bit, but here we go. Oh, that's not good. Delta G is equal to negative. Why? Final minus initial. You take a final number that's smaller than a larger number. If you subtract a larger number from a smaller number, guess what you get? A negative number. Oh my gosh! So the signs are critical here. The point I'm making is the signs are critical. I told you that earlier for Q and W. It's critical for everything. Okay, so here we go. Let's continue on. Okay, so this is the first thing. Is just the total energy is what rules it. Whether something's going to happen in your system. Does your system become more stable? Okay, not the universe, the system. That's what we're interested in chemistry when we do a reaction. Okay, let's look at the bottom. Both matter and energy naturally tend to disperse. Okay, now this is a general observation, and this is what's going to back us into this whole idea of is something spontaneous. All right. There's two things we observe. Balls roll downhill, but there's another thing that's a general rule that's not normally talked about until this point, either in a physics class or this point in your chemistry career, as it were. Okay? And that's matter and energy tend to disperse. Energy tends to become less usable, right? The energy at the top of a dam, okay? It's all stacked up, but as you let the waterfall run over the mill, it turns this board, which turns a wheel, which allows you to grind the wheat or whatever you're grinding. But guess what? Then the water goes down below the wheel. And guess what? It can't turn it anymore. It spreads out and it's not usable. It's less usable. See, as the water flows downhill, it's not really usable down here. It's only usable up here. Okay, so a general observation is, but the same is true for chemical reactions or anything. Once you run a reaction, that energy is less usable. The heater from your refrigerator, right? Your motors generate a certain amount of energy that's used to cool your refrigerator. Yes, goes to the engine, the little motor that's inside your refrigerator back, and then generates what? Heat. Well, really? Well, yeah. Well, so that energy was lost. That energy couldn't be used. That energy from the friction of your motor, it's part of the overall energy you used to make the ice, but it's no longer usable. That energy just gets thrown out into the atmosphere. So this is a general observation that the wizards of smart came up with, and those are the two big factors. Energy tends to decrease and it becomes less usable. Well, shoot, we need a way to measure that. Okay, because that's not heat energy, it's usableness. Okay, so that's this idea of entropy. Okay, so that's what entropy is all about. Okay, so Now let's kind of put entropy in some simple common terms. And this is what you really need to know. This is what's going to serve you well. Okay, as far as the concept goes. This. Some people would tell you that's not true. Exactly, but hey, this is the way I think about it, and it works for all the problems I come across in Gen Chem. So here we go. People debate this, but don't. Just don't. Here we go. Entropy can be thought of as a measure of disorder. There we have it. That's another statement of, that is another way of saying energy is dispersed. It's less usable. It's dispersed. See, the energy from the heat of your refrigerator, the energy came out the back of the refrigerator, just started filling the room up, and it went everywhere. Okay, so there we go. So when we say matter or energy is dispersed, what do I mean? It spreads out. It's self-diluting. It expands. It takes up more space. It becomes more uniform. I don't know. You just use whatever phrase you want. But we need to have some way to express that mathematically. It's pretty easy to express heat mathematically, but how do you express this expansion, not as usable thing? How do you get your hand, how are you going to measure that? Okay, well, they actually do. They have this thing called entropy. And the word they give to it is called entropy. And what you're doing is you're measuring the disorder. Okay, so let me give you 3 words that I use. Depending on the question, how it's worded, some words I found out really help me more than the word disorder. So here we go. I'll give you Dr. Stevenson's 4 terms for entropy. When you read a problem, can you see if something's becoming more disordered? Can you see if things are becoming more random? Can you see if things are becoming more chaotic? Do you see if there's more freedom? Those 4 words. For example, freedom. What's that got to do with any of this thing? Okay, say we have a bottle of perfume. Yep, and the cap's on there. It's a little bitty small, expensive, whatever it's paid now, $100 a half an ounce or whatever. I know I'm in the wrong business. All right, so let's say it's there, and when you open the top of the perfume, you smell it in a few seconds. Why do you smell it? Well, you smell it because the molecules jumped out of the bottle and went across space, translated across space, and hit you in the nose. That's why you smell it, because those molecules actually hit you. Well, what was the driving force for the molecules jumping out of the bottle and hitting you in the nose? Why did it do it? Why did the molecules do it? Because actually, if you look at it, the vaporization is actually an endothermic process. It's not favorable. If you just look at heat, you say, wait, perfume won't work. Why? Because the molecules are jumping out of the liquid into the vapor. When you take something out of the liquid into the vapor, it takes energy, so that's unfavorable. But I didn't add any energy, so it shouldn't happen. But it does happen. Why? Because of the entropy term. The entropy is the compelling factor. Well, what do you mean freedom? Well, the molecules, think about it as a cage. The molecules were caged in a little bottle, and you open the bottle, and now they can run around anywhere in the universe. That's a whole lot more freedom. It's a jailbreak. Yes? So you're in a 6x6 cell, and all of a sudden, you can just travel anywhere in the world. Okay, that's entropy. Yes? You got more entropy. The key to notice here is this is disorder. Entropy is not a measure of order. It's a measure of disorder. If you increase entropy, which is a delta S, if you increase entropy, what you're doing is if you're increasing entropy, oh boy, that was bad, but that's supposed to be a plus sign. If you're increasing entropy, you're what? Increasing the disorder. Because remember, Mother Nature likes this. That's what you got to get in your head. We like things to be ordered. We need the bed made. We don't want the bricks to fall off the side of our house in a state of disorder. No, we want things ordered. Mother Nature wants them disordered. And now you know why you're going to get old, and your teeth are going to break, and your house is going to fall down, and your car's going to break, and your body's going to tear up. Why? Because Mother Nature tends toward disorder. And I'll tell you what's going to happen. Ashes to ashes, dust to dust, right? Hey, Those never were truer words spoke. That's because in this world we live, Mother Nature tends toward disorder. And let me tell you what's going to happen given a long enough time frame. I'm going to die, then I'm going to start decaying, and then it's going to get worse and worse. And guess what's going to happen? I'm eventually going to go back to individual molecules. Really? Yeah. Mama Nature is going to take me back to dust. She's going to take me back to molecules. Mother Nature, the disorder thing wins. And that's why the world is so tough. Because we keep trying to order things, and Mother Nature keeps trying to disorder them. And there we go. There's life, okay, in almost every aspect, right? Okay, so that's why entropy is a really cool concept. You can talk about entropy of politics. You can talk about entropy of anything. What you're really talking about is disorder or chaos or randomness or freedom. That's what entropy, but what's weird is you can actually measure that at the chemical level. Okay, so it's a kind of a tough abstract. Okay, we're not going to go over this. You're just going to do plug and chug here. All right. So, but this is the definition of entropy. Now, you're going to calculate it the other ways, probably using those methods I showed you earlier. But there is a definition. I don't want you to spend a whole lot of time on the definition. This is kind of a sticky wicket. Okay. But here we go. So we need a definition. So there's what entropy is. Well, I thought entropy didn't have anything to do with heat. Well, yeah, it does have heat. Entropy is actually the heat energy at a given temperature. Okay, that's what I'm saying. If you think through this stuff too much, it'll make you crazy. It'll make you crazy. Okay, but I just want you to know that, and you'll see why this is important in a second with one of the examples. Okay, so enthalpy changes for a system. Okay, so what does reversible mean? Okay, so some of you may know I've had a class where they explain that, but reversible is for a system which never loses equilibrium. Okay, so let's look at equilibrium. Remember, we might have a solid here and a liquid here, say, and we're at equilibrium. All right, so at any point on this line, we're at equilibrium. So we would say, if we're on this line, that change is reversible, because at any point in time, we're at equilibrium. Okay, well, let's say we couldn't measure it very well. And let's do a zoom up on that. And let's say our curve is actually, oh boy, this is just a horrible drawing. Okay, so I'm trying to draw this curve kind of pixelated, where it's not smooth. Okay, so this is not a reversible. This is step change, right? This goes up, and then it goes over and up and over. And I'm defining that line, but it's not reversible. It actually is discrete steps. Now, the idea, by the way, is to get these steps so small that it looks like a smooth line. Like an old television set, right? The pixels are real big. Yep. And you could, if you got close to the TV, you could see the dang pixels. So I could see them. Why? It's pixelated. And we pixelate things all the time. Okay. So how do you, what's the whole thing about high definition? What's that all about? Well, it's making these pixels so small that they just look continuous. That it just looks like one smooth thing. They're so small and together, you can't tell the difference, okay? That's a good analogy between something that's reversible and something that's not. Something that's pixelated, not reversible, and something that's smooth, something that's reversible. Okay. Don't go, you may want to just do that for plug and chug, but here we go. The way entropy is done is they use a statistics thing. Okay, so I'm just going to tell you in case you read it. Let's say we have we start out with a chemical or 4 dots here, and we have 2 different containers, right? Okay, so what are our states we could have? So we're talking about freedom here. We could have 2 here, and 2 could move to this side of the container, or we could have 3 here and 1 on this side, or 1 could stay here and 3 could be here, or none could be here, and all 4 could move to this side of the container. Okay, so you have a bunch of these possibilities when you look at molecules moving around space. Just so you know, those are called microstates. Yes? So they do this. What is entropy? Well, depending on how many microstates you have, that tells you the probability of where they're going to be. It tells you how disordered it's going to be. So if it's whether it's homogeneous or whether they're all lumped up, you can see that's a very different thing, okay? Well, That's why when you have a glass of water or something, you don't wind up with all the water molecules on one side of your beaker and none on the other. It's not just lumping to the side there. Why? That's an entropy thing. That's a statistical thing. That's a microstate thing. Okay. So you can kind of just look over that real quick. I just want you to know the equations for that one. That's it. We're not going to drill down on it. I just want you to know ultimately entropy divided by microstates. Okay, so what you need to know is what a reversible change. You need to know the definition for entropy. It's the Q reversible, not Q out here. It's Q reversible divided by whatever temperature you're doing that measurement. Okay, there's a second definition. This is the one based on temperature and Q. This is a second definition that's based on microstates. Got it? And then of course you could set this S equal to that, and you could do some funky things with that equation. You could set them equal to each other, and then you get this. Yes? And so then K crosses off, right? You do those together, so you get, and then there we go. Okay. So we're not going to deal a lot with this, but you'll see why in a minute. It's important to the concept. Okay, so what do we have? Maybe 3 minutes to go. Okay, so I do want you to read ahead on this. But what we're going to do when we return, let's see. Oh, let me finish this up. Okay, so the book talks about microstates. This is just kind of work through this problem. So if I take something really simple, this right here, atom 1 and 2, it could be on this side. 1 could be there, 2 could be there, 1 and 2 could both be here, 2 could be here, and 1 could be here. So there's a half a chance that this will happen, one of these, where each one of them's at a different box. There's only a quarter chance this will happen and a quarter chance that'll happen. So this is a statistics thing. If you like statistics, this is your ball game. This is how you're going to want to think about it. So plugging into that equation I gave you, and that's a constant that's given. Okay, so that is a set constant. So delta S is equal to K log of, there's a total of 4 microstates. Yep. Okay, so Z squared. Yes. Okay, so what are we looking for? Log of 4 is 1.39. So I could actually calculate delta S for this based on microstates. Okay, so count the interchange in line 2 particles in one box to expand into 2 boxes. Okay, so you got 2 particles, and this is how they did that. They looked got the number of microstates. Okay, so there we go. Right. Microstate distributions. The book spends a lot of time on this. If you understand this one slide and know how to plug it into that one equation, you're golden. Okay, so we're going to stop it there.